let's try to solve this problem over here. So the atomic mass of helium-4 is 4.002603 U, and the atomic mass of hydrogen is 1 hydrogen is 1.007825. So they're giving you two atomic mass over here. One is the atomic mass of helium-4, so this value here is in the unit of AMU, the atomic mass unit, but this is the atomic mass, not the nuclear mass. So always remember, when you're solving questions related to the mass defect or binding energy, be very clear whether you are given with the mass of atom or the nuclear mass. Okay, so they give you atomic mass over here, then also they give you the atomic mass of hydrogen. The atomic mass of hydrogen is also given on the side over here. So I think they're sort of trying to nudge you to solve this question using the mass of hydrogen isotope. Okay, there's many ways to solve there are two ways to solve the questions if you are given with the atomic mass. One is you take the atomic mass over here and you remove the electrons, the mass of electrons that are orbiting around the nucleus. You remove the mass of electrons orbiting the nucleus, then you can get the mass of a nucleus. Then from there on, you try to determine mass defect. Okay, that's one way. But another way is to use the equation another equation that has hydrogen mass in it, the mass of hydrogen in it. Okay, so I think this is the approach that they wish us to go for. So we'll be using the equation that has mass of hydrogen in it. Okay, to understand why can you substitute the mass of proton with the mass of hydrogen, please refer to the derivation video that we have in this playlist over here. Okay, so use atomic mass unit instead of kilogram, so they don't want you to use kilogram. Obtain the binding energy of the 4,2 helium nucleus in MeV. So now they want the energy in the unit of MeV. Okay, so let's try to solve this question by determining the binding energy, the mass defect first. So the mass defect over here, technically you have three equations to pick from, but the equation that has mass of hydrogen in it will be ZmH. Instead of multiplying the mass of proton, we are multiplying the mass of hydrogen plus the number of neutron multiplied by the mass of one single neutron. This will let us know the mass of all separated constituents. When they are separated, what's their total mass? They can minus the mass of atom of the nucleus that we're interested to find its binding energy. We're interested to find the binding energy of the 4,2 helium nucleus. So that is our interest over here. Some students might be confused that we are finding the binding energy for hydrogen. No, they give us the they give us the atomic mass of hydrogen just for us to know that what is the mass of hydrogen over here. Their interest is still binding energy of the 4,2 helium nucleus. So our Z, our N over here have to be done with respect to the helium atom that we have here. So since this is 4,2 helium, again, you can have your mass number equals to 4, your number of nucleon equals to 4, your proton number or your mass or your atomic number to be equals to 2. So your number of neutron will be equals to A minus Z, which is again 4 minus 2 equals to 2. Okay, so once you have everything cleared out, so you can write in 2, the mass of hydrogen 1.6007825 plus there's 2 neutron, each neutron 1.008665. So this is mass of separated constituents minus the mass of atom. The mass of atom is given over here. We are not using the mass of hydrogen. Again, our focus is the binding energy of the 4,2 helium nucleus. So we are going to put in the atomic mass of the helium nucleus. 4.002603. Okay, so this part here is the mass of separated constituents. This part here is the mass of atom. So if you minus it, you get answer 0.030377. Okay, please notice that I have 6 decimal place for our masses over here. So my mass defect here should follow the same 6 number of decimal place over here. But again, I'm going to write the unit, be very clear, the unit is in atomic mass unit. Okay, now we can determine the binding energy. Binding energy is just taking the mass defect multiplied by C squared. But for our mass defect over here, you have to be very clear, since the mass defect is in atomic mass unit, you have to use method 2 to determine the binding energy. Please refer to method 2 in the previous example. Basically, you convert it from atomic mass unit to MeV over C squared. So you know that 1U is equal to 931.5 MeV over C squared. So this process here will let us know the mass defect, but in the unit of MeV over c square. Then you multiply by c square, you are able to get the binding energy in the unit of MeV. Why is it so? Because you can see that the U and the U, they are on numerator and denominator, can be crossed out. C square and C square here also, one on the denominator, one on the numerator, can be cancelled out as well. So if you proceed through to calculate this, you get your binding energy to be equals to 28.30 MeV. Okay, so this is the faster shortcut way of determining binding energy, and it can only be used if your mass defect can be converted into MeV over c square. Once it's converted, then the c square can cross out, the u can cross out, then you can get your binding energy in the unit of MeV. Okay, so a very relatively straightforward question. Just to demonstrate to you, there are equations that do not use the mass of proton, instead use the mass of hydrogen. This equation can only be used if you are given with the mass of atom or the atomic mass rather than the mass of nucleus or the nuclear mass. So that's it for this question. Thank you very much. And if you refer to the previous example, I believe it's the same isotope, right? So since they are the same isotope, you can compare the binding energy with the previous question. Yeah, the binding energy for the previous question is 28.34 MeV, and here is 28.30 MeV, so it's sort of the same. So showing that different methods will result in similar answer also.